Hey everyone, and welcome. So think about this for a second. The apps on your phone, the software in a modern car, even the flight controls of an airplane, they're all making thousands, maybe millions of decisions every single second. But how? How does a bunch of code, well, think? Let's get into it. It really all boils down to this one question. How does a program, which is just a long list of instructions, figure out what to do when things change? The answer is actually pretty simple, and it's something you already do every day. At its very core, code makes decisions just like we do. It checks if something is true, and if it is, it does one thing. If not, it does something else. So on the left, you've got a simple instruction in plain English, and on the right, that's pretty much exactly how a programmer would write it. It's a direct translation of how we think. And the main tool for this job is the if-then-else statement. This is the absolute cornerstone of programming logic. You can think of it like a fork in the road. If a condition is true, then you go left. Else, you go right. Simple as that. But here's the catch, right? One fork in the road is easy, but modern software isn't just one fork. It's a massive labyrinth of thousands, even millions of these choices, all tangled together. And that's where we fall into the complexity trap. The real trouble starts when you nest these decisions. You have an if statement, and inside that there's another if statement, and maybe another one inside that. Every single layer adds a new level of logic that a developer has to juggle in their mind. This right here is a perfect example, the classic dangling else problem. Just take a look at it. Can you tell for sure if that else statement belongs to the first if or the second one? It's ambiguous. And that kind of ambiguity can lead to some really catastrophic bugs if the programmer and the computer disagree on what it means. Early on, programmers came up with a fantastic name for this kind of tangled, hard-to-follow logic. They called it spaghetti code. And it's a perfect description, right? It's just a messy plate of code where everything is intertwined, and it's a total nightmare to read, debug, or change. And this isn't just some old-school problem. Here is a real piece of code from a real application. It's a function for processing a transaction. Just look at all those nested if statements. To understand what's happening here, you literally have to trace every single possible path. It's like a jungle, and it is the perfect hiding place for bugs. So we've seen how code can turn into a tangled mess. But what if we could measure it? Is there a way to put an actual number on how complex a piece of code really is? Turns out there is. Way back in 1976, a guy named Thomas McCabe came up with a metric he called cyclomatic complexity. It's a formal way to count up all the unique, independent paths a program can take. The higher that number, well, the more complex your code is. Now, with a name like cyclomatic complexity, you'd think the formula would be some crazy equation, right? Nope. It's unbelievably simple. In most cases, you just count the number of decision points, your ifs, your while loops, and you add one. That's it. So let's look at our examples again. A pretty simple function to validate user input might have 3 if statements. That gives it a complexity score of 4. Totally manageable. But our spaghetti code for processing a transaction, it has 10 decision points, giving it a complexity of 11. That is a huge difference, and it's a major red flag. So what does a number like 11 actually mean? Well, for a developer, it's a giant warning sign. It means that code needs way more testing. It's screaming to be refactored, which is just a fancy word for breaking it down into smaller, simpler pieces. It means it's mentally exhausting to work on. And most importantly, the risk of bugs hiding in there is way, way higher. Okay, so now that we get what makes code complex, let's look at a really clever trick that computers use to blaze through all these decisions without wasting any energy. It's a technique called short circuit evaluation. Honestly, you can just think of it as the computer being strategically lazy. It reads a logical statement from left to right, and the absolute second it knows the final answer, it just stops. It doesn't do any extra work it doesn't have to. Here's a perfect example with a logical and. The computer needs to figure out if X and Y are both true. So first, it checks X. Now, if X is false, does it even matter what Y is? No way. The whole thing is already false. So it just stops right there. It only bothers to check Y if and only if X turns out to be true. It's a tiny optimization that saves a ton of processing time. Okay, so we've looked at simple choices, tangled complexity, and these clever shortcuts. Now let's bring it all home and talk about why this stuff really matters, especially in situations where lives are on the line. I want you to read this. This isn't a line of code. It's a safety requirement for a medical infusion pump, a machine that delivers medicine to a patient. The logic here has to be absolutely perfect. One mistake, one dangling else, or a bug hidden in some complex function could have unimaginably serious consequences. For systems like these, you can't just hope the code is right. You can't just run a bunch of tests and cross your fingers. You need to have a mathematical guarantee that it is correct. You have to formally prove that the code does exactly what it's supposed to do, under every possible circumstance. One of the most powerful ways to do this is with something called Hoare logic. It's a formal system that lets computer scientists use pure mathematics to prove that if your program starts in a known good state, that's the precondition, then after the code runs, it is guaranteed to end in another known good state, the postcondition. It's how we can be sure the code is safe. And this is where everything comes full circle. You can't apply these powerful mathematical proofs to spaghetti code. It's just too tangled, too unpredictable. So managing complexity, keeping that cyclomatic complexity score low, isn't just about being a tidy programmer. It's about making it possible to build software that we can actually trust with our safety. So we've seen that all software, no matter how complicated, is built out of that one humble building block, the if-then-else. But the real profound challenge is making sure that when you stack up millions of those simple choices, they always add up to the right one, especially when it matters most.